Dear learners, welcome to the first lecture on BSc Mathematics. I am Amit Wadile from the Department of Mathematics, and today we will be discussing the Rolle's theorem from the calculus of one variable. So what is Rolle's theorem? So the statement of Rolle's theorem is the function fx is, first condition, continuous in closed interval AB. Second, differentiable in open interval AB, that is, it is differentiable at all points of the interval except the endpoints A and B. And there will be one more condition which says that the function value at the point A is equal to the function value at the point B. That is, the function, the two endpoints, the function taking the same value. Then, in this case, the Rolle's theorem says that there exists at least one point C belongs to open interval AB such that f dash of C is equal to 0. Means there will be a point C where the slope of the tangent is 0 or the slope of the tangent is parallel to the x-axis. So now, if we go through the geometrical interpretation of Rolle's theorem, so let's consider the function. Let's consider the function which is plotted in the x-axis and in this y-axis here. There is a point A, and the function value at the point A is here, that is f of A, and there will be a point and the same value at the point B, the function is taking at the point B here. So this is continuous and differentiable everywhere. This function is continuous and differentiable everywhere, and this theorem says that there will be at least one point where the derivative will vanish, or the tangent will be 0. That is, the slope of the tangent is parallel to the x-axis or the slope of the tangent is 0. So clearly we can observe that there is a point A somewhere next to the A. At the point, the slope is the tangent is parallel to the x-axis. In this function, there is another point where the slope of the tangent is parallel to the x-axis. So this theorem says that there will be at least one point where the slope of the tangent is parallel to the x-axis. But in this case, we are getting more than one point where the slope of the tangent is parallel to the x-axis or the slope of the tangent will be 0. So if we go through the proof of the theorem. So proof of Rolle's theorem. Since fx is continuous in closed interval AB. But we know that the theorems on continuity, every closed and bounded, every continuous function on closed and bounded interval is bounded, and every continuous function and closed and bounded interval attains its bounds. So by these theorems, or by using these theorems, fx is bounded in closed interval AB and attains its bounds at least once in closed interval AB. Let, if we take capital M is equal to supremum of f and small m is equal to infimum of f, then there exists alpha and beta which is belongs to closed interval AB such that f of alpha is equal to m and f of beta is equal to capital M. Then m is equal to f of alpha is less than or equal to f of x is less than or equal to f of beta is equal to capital M. This is equation number first. So now consider the first case. Let capital M is equal to small m, that is supremum value of f is equal to the infimum value of f. So in this particular case, now we think about the situation where the minimum value and the maximum value, that is the supremum of f and infimum f, are same. So in this case, clearly there is no change in the function value. That is, for example, geometrically, if we draw the line and we get the point in this way, so this is a point, that f of a, and this is b point, that f of b. So there is no change in the function value. So in this case, the function is constant in closed interval AB. So we write m is equal to f of alpha is less than or equal to fx is less than or equal to f of beta is equal to capital M. So that is f of x is equal to capital M for all x belongs to closed interval AB. And we know that the derivative of constant function is 0. So we write f dash of x is equal to 0. F dash of x is equal to 0 for all x belongs to closed interval AB, and this proves the theorem for the case first. So now we consider the second case. In this case, let supremum value of f is not equal to infimum value of f, that is, let capital M is not equal to small m. Since f of a is equal to f of b, so one of the value small m and capital M must be different from f of a and f of b. Must be different from f of a and f of b. So let capital M is not equal to f of a, then f of a is equal to f of b, so capital M is not equal to f of b. So this implies that f of beta is not equal to f of a and f of beta is not equal to f of b. So from this we write, this implies that beta is not equal to a and beta is not equal to b, then beta belongs to open interval AB, because beta are not the endpoints. So from the condition second of the theorem, f of x is differentiable at beta. The function is differentiable at point beta. Fx is differentiable at point beta. Then by definition of differentiable at a point, limit of x tends to beta minus fx minus f of beta upon x minus beta is equal to limit of x tends to beta plus fx minus f of beta upon x minus beta is equal to f dash of beta. But this is equation number second. But from equation 1 we write f of x minus f of beta is less than or equal to 0 for all x belongs to closed interval AB. If we take x less than beta, then limit of x tends to beta minus fx minus f of beta upon x minus beta is greater than or equal to 0, and if x greater than beta, then limit of x tends to beta plus fx minus f of beta upon x minus beta is less than or equal to 0. Now taking the limit as beta tends to 0 on both sides, we get, now taking the limit as x tends to beta on both sides, we get limit of x tends to beta minus fx minus f of beta upon x minus beta is greater than or equal to 0, and limit of x tends to beta plus fx minus f of beta upon x minus beta is less than or equal to 0. But from the equation 2 we write f dash of beta is greater than or equal to 0 and f dash of beta is less than or equal to 0. But out of these two conditions, we cannot say that the function is less than or equal to 0 or greater than or equal to 0 at the same value, at the same time. So the only condition is the f dash of beta is equal to 0 for all x belongs to open interval AB. So thus there exists at least one point C belongs to open interval AB such that f dash of C is equal to 0. Hence the proof. Thank you.